In last class, we talked a lot about the physics and then the chemistry and the dynamics of plasma-assisted combustion. Today, we try to take two classes and talking about the diagnostics and the modeling. And the diagnostics is the key that help us to quantify what is the plasma properties and what are the species produced as a function of time, so that allow us to validate the model and understand what is the physical chemistry of the process. So I talk about three things. That the first is that how to measure the plasma properties and then the kinetic process. And then secondly, to try to do the experimental measurement in plasma-assisted combustion and to detect the active species as a function of time, and to do some kinetic study of plasma-assisted combustion. Not working? Okay. So the first thing we talk is that how to measure the plasma properties. In order to, for example, develop a model or to understand how plasma enhance combustion, the first thing we need to know that what is the electron number density and what is electron temperature. So that is that the higher the electron temperature, and they change the reaction cross-section areas and change the reaction pathway depending on electron temperature. So measuring electron temperature and electron number density is something different from what we normally do in combustion process. So one of that a method was developed is that called a Thomson scattering. It's the extension of a Raman scattering or Rayleigh scattering. You try to measure that electronic scattering and in a plasma process. For example, if you have electrons and if you're shining a laser, and the laser frequency basically will be modulated by electronic motion, just like a Doppler broadening, right? So if you measure that the broadening, you should be able to measure that the average temperature in the field. So for example, imagine that you have a laser propagating in this plane, and then you have for example, a polarization of the electronic field of the laser polarizes this angle. And your detection plane, for example, is XZ. And you try to detect that the scattering and from that the polarized laser propagating in this direction. So the power of scattering of PS is a function about what is the theta of that a scattering angle to the laser propagation direction. And then what is that the angle of phi between the polarization angle and the observation plane. So this is given is the equation of powered scattering. And the number density of the photons, for example, you can observe from the scattering certainly is proportional to the cross-section area of that electrons scattering. And the proportional to that the length of the detection. For example, you want to detect that the beam at 1 millimeter, 2 millimeter, the large area, you detect the laser beam is linearly proportional to the photon numbers. And also that the photon collection optics, for example, eta, is that define how far of the objects and how big your camera. And then the quantum efficiency they determine here. And then this one is normalized the energy of that you can see here is the laser energy. So if you know this one, you can measure that the scattering signal. So the scattering signal, in order to extract that the information of electrons, and you need to do a reference. The two types of scattering, one is that electron scattering, the other one is the molecular, for example, Raman scattering. So the way to do it is that using a similarity of that the Raman scattering and then Thomson scattering. So if you know the signal of that a electron scattering and then that the a Raman scattering, so you take that ratio and then using that the signal calibrate for the Raman scattering, you get the electron number density. So I'll show you an example of that. So this is that the the way to that using a Raman scattering of nitrogen, sometimes using helium, if we wanted the background noise to be lower. So to get a Raman scattering signal, and then you take that the signal of electron scattering, and you make it normalize it, and you get that the electron number density. So for broadening, that Doppler broadening, you can say the line width broadening is proportional to that the relative velocity of the electrons relative to the photon. So using that the broadening of the width of the laser scattering beam, so you can detect that, take a inverse of this equation, you can get that electron temperature. So this is that one of the advanced method to measure simultaneously electron number density and the electron temperature. So here that we have a graduate student at Princeton, Tim Chen, he's sitting there, and he tried to develop this Thomson scattering experiment. So you have a Yak laser with the 10 Hertz, and then you go to mirror reflected. Here is a long focal length with probably a meter long about focal length, and focus the laser beam and into the plasma area. And then here that you have some kind of a structure to block the scattering of that the signal reflection on the wall, so that you know that the relay scattering or the Thomson scattering, the signal is really weak. So here is the beam damper, and then you have a lens to collect the light of the scattering and the vertical to the laser propagation direction, and you collect the spectrometer, and then you have some kind of filter to filter that the relay scattering, and you took that the Raman scattering and Thomson scattering signal. So here is that what is that the experimental result, and probably this is by Brugman, and you can see that this is that the Raman scattering. So you can see this is using this signal as the references of that to measuring that electron number density, and here is that is the signal of that a Raman signal and Thomson signal together. So if you subtract that the Raman signal, you get the Thomson scattering, and then this is that the filter. You filter that the relay scattering in the center, and this the broaden the width will be that the electron temperature. So that is the way to measure that a number density and the temperature. So this is an example that Ohio State that Walter Lampert and also that Igor Adamovich. And then using this method, you successfully measure the number density of the and then electron temperature. I show you an example here. So this is at the discharge. Basically, the 200 tall is about a sphere and a discharge of helium environment, because helium environment has very low scattering noise and very easy to ionize at 200 tall. It's about 1 centimeter separation distance. So here that the signal they take is that you see this is that the green line is the Thomson scattering signal, and this dip is because that they blocked a relay scattering. You can buy a filter, you can buy a mechanical stick, and to block that signal. So this is that the shape is a Gaussian fitting. You can fit in this curve. You can measure that electron and temperature by taking the references with that the Raman scattering of helium, and then you can get the number density of electrons. So so here you can see that this electron temperature basically is a line width and the broadening, and so using that you can calibrate that the system and compare with the numerical simulation. So this is the actual signal with nitrogen Raman scattering. So using this one as a references for that electron number density measurements. So the next thing that you can see that the Thomson scattering measurement of a nanosecond discharge in a hydrogen helium system at 100 tall. We always do that low pressure is because the plasma is more diffusive, allow you to measure that enough spatial resolution to measure the local temperature and the electron number density. So here is the signal, and the Thomson scattering signal, and you can do a Gaussian fit, and this Gaussian fit it gives you that the width of the broadening and give you that the temperature is about 2.0 eV and number density is 10 to the 14th. So which is pretty high, and number density 10 to the 14th is because that this is at the with the helium dilution environment. And then if you adding, for example, oxygen to it, and then will you expect the number density decrease or increase? From what we learned yesterday? Decrease. So this is that experimental result. You can see that with the addition of oxygen to the system, you see that the electron number density decrease, and the electron temperature will decrease as well. So this is that they show you that in a very clean environment, particularly in a helium and oxygen system, and you can a Thomson scattering is a very effective way to measure the number density and then a electron temperature. But if you have a dirty environment, for example, if you have large alkanes, and if you have probably even for high temperature of nitrogen, you may have a very strong background noise. That how do you deal with background noise to make a Thomson scattering probably be very critical in the measurement. So here is that measurement, how that the number density of electrons as a function of time for two pulses. And these two pulses, one is at the time 0, the other one is the time 400. The red one is at the electron number density. You can see here. And this is that the line is a prediction. So you can see that the predicted electron number density and the measured electron number density and the temperature, they agree reasonably well in this helium-oxygen system. The plasma model in air plasma is reasonably well studied in the system. The really key challenge is that the kinetics coupling with combustion process. There, that the reaction pathway is very less studied. So you can see that the electron temperature in this kind of nanosecond plasma at that condition is around about 2.5 eV. It's rather not very high, surprisingly, because that the collisional energy transfer reduces the electron temperature rather quickly. So remember the measurement probably, I think that the measurement is probably 2 nanoseconds. If you have a nanosecond plasma, during the first 2 nanoseconds, probably electron temperature is very high. But the camera, you cannot resolve within the 2 nanoseconds. So another example is a measurement in Hokkaido University by Sakai. Sakai's group basically tried to do a micro discharge, and basically needle to needle, and you can see that it's a microwave discharge. And you try to using that a Thomson scattering to measure the electron number density and temperature in a helium environment. And what did it do? That this time that when we measure the electron number density, they're using that the Raman scattering from helium as the references. And if you're looking at the results, so if you're looking at the result that the scattering density as an electron energy, you can see the distribution like this shape. It's a little bit of long tail, showing that the electron energy distribution is not a Maxwell distribution. It is a non-Maxwell and Boltzmann distribution. The average temperature is about a 2.0 electron volt. And then if you change the system pressure, if you change it to 10 atmosphere pressure, because a microwave is a very effective discharge to discharge at high pressure. So you increase the system to 10 atmosphere pressure, and then you can see the temperature, electron temperature almost slightly increase, not very much. And in terms of, I'm not quite sure why the temperature increased at the pressure. So when you have a higher pressure, the collisional quenching of these electrons the collisional quenching should be very fast. So electron temperature should decrease. So I don't understand what this figure, why they measure that almost, I don't know the uncertainty of the experimental measurement, but that it seems to be slightly increased, or it does not change at all. But if you're looking at the electron number density, it's decreasing with the pressure. You can see that the quenching is pretty fast. So if the electron quenching pretty fast, that means that energy transfer between electrons and then a neutral molecule should be very fast. So the temperature the collision is very fast, the mean free path is shorter, the electron temperature should be lower. So this one I pretty much question. I didn't get a chance to talk to him. So why they're showing that the electron temperature has a positive dependence on the pressure. So this is that one way. The other way that you measure electron number density, and you measure that electron temperature. The other thing that is the electrical field, the E over N. So electrical field measurement is very important. For a long time, it was very difficult to measure electric field. You cannot because of the sheath effect. At the two electrodes, you have significant voltage drop at the very thin layer, which is less than a micron meter. So you have no way you can measure that the voltage drop within the sheath. So the question is that how can we really correctly measure the electric field as a function of time in the field? That was really difficult. Recently, that my colleague said, Professor Myers, and he really discovered a new way to measure an electrical field. What they did is that they're basically using some femtosecond laser and to generate a laser-driven electrical field to generate a second harmonic of the molecules. Let's say you have oxygen molecules. So oxygen molecules, basically two atoms, they are symmetric, right? So you don't have a second harmonic waves because they are symmetrical atoms. But if you put a strong laser, very strong laser is a electronic magnetic wave. So that will perturb the electron orbiter to generate unsymmetric effect in the direction of laser propagation, with propagation directions. So you generate a second harmonic due to the external electric field. So in this method, he basically says that I have a laser coming here, and then this is the external electric field generation, and this will perturb the symmetry of the molecules, and then allow it to generate the second harmonics. Once you generate a second harmonic, you split it from the original laser, and you're basically measuring the second harmonic detector to measure how strong the second harmonic waves production. So in this way, that he should be able to measure the second harmonic wave signal is proportional to the square of the number density proportional to the pumping power, because the second harmonic is proportional to the square of the laser intensity. So in this way, that he can quantitatively measure the signal response as a function of the field strength. This is the voltage per centimeter. This is the electric field. This is the calibration. You can see that using a quadratic fitting, that the signal and then the measured and then an actual field can be fitted in a curve. You can use this calibrated curve to measure the real electromagnetic field in a plasma system, for example. So this is what he measured, that the electrical field as a function of time, and the resolution you can see probably a few nanoseconds that they use this method. So this using the femtosecond laser to drive a second harmonic generation from molecule provide a effective way to measure the electric field. So the challenge here is that you need a calibration, because you don't know how much the second harmonic is generated for particular molecule at different conditions. It highly depends on collision, depends on a relaxation process. So you always need to have a calibration process. So this Thomson scattering, and then the femtosecond laser, a second harmonic generation, they give you potential methods to detect the properties of plasma field: electron number density, temperature, electric field, right? With this three information, you should be able to do a numerical simulation and to validate it with the experiment. There's some alternative way to do this as well, and then we try to move forward. So this is the measurement at Ohio State and Igor Adamovich, and also the Walter Lampert group. And they basically try to, using this method, to try to measure a two-dimensional a nanosecond pulse discharge. Let's say you put some kind of a knife edge and above a quartz dielectric material, is probably the quartz, and then you put a nanosecond discharge and you try to measure that the electrical field and the electron temperature distribution and as a function of time. So here that they basically say if you have a view from side view from this direction to the left to the right, this is their side view. So you can see the laser beam, the location. You can move the laser beam in this direction or that direction. You can probe in that local electron temperature and number density. So here is the result. It can show you that you can measure that the voltage change. The voltage basically, the black one is the voltage, and the decrease and rise. So this is at the 100 nanosecond, probably a pulse width. And you can see that the current and is decreasing and rising along with that the voltage. And then this is a calculate the coupled energy. The question is that what is that the plasma properties? So this is that the video basically showing that how the plasma generates. So if you look at that the side view, that is the view and in a direction parallel to the surface of that knife edge, you can see that the plasma is generated and then they propagate to the both sides of the edge. And if you're looking at from front view, and this is the quartz, this is a knife edge, you can see that the plasma is propagating between the knife edge and then the quartz. So there's a lot of a streamer is forming between. It's not really uniform, even with this nanosecond discharge. So if you look at the top view, you can see that the plasma also spreading to the both sides of the surface of the front and back surface of the knife edge. So what it says is that with this method, and then they try to generate a high pressure discharge in high pressure fuel mixture, because the high pressure plasma is easily transferred into a thermal plasma. Not only you need a very small gap, but also you need a very short pulse to avoid that the transformation from a non-equilibrium plasma to a thermal plasma. And this is the experimental result. The result basically, again, they show you the voltage current is here. And in this one, they show you the measured electrical field in the x direction, in the y direction, and then this integrate of a magnitude based in x and y direction. So this experiment basically potentially show that this kind of a laser-driven second harmonic method has the potential to measure the electrical field. And as a time-dependent measurement, for example, you can see this is at the 50 nanosecond. The resolution is a few nanoseconds to allow you to measurements. So this is a very powerful way to measure electrical field in a plasma a discharge. So except this a direct laser measurement of that the second harmonics or the Doppler broadening, and people have been in plasma field have been using emission spectroscopy directly estimate what is the electron number density and what is the electron temperature. And for example, argon, and because the argon is very easy to be discharged and in a plasma field. And this is at the energy level of argons. This that 3p, this level, that emission between that the 4d and 4p and 4p and 4s, this emission is often used and to measure that the electron energy or number density. For example, this is an experiment and did at the Chinese Tsinghua University by Yi Kampu's group, and he measuring that the pin-to-pin discharge in probably in argon and helium argon mixture, because in the gas in air you always have some kind of moisture of hydrogen or water. When the water in the plasma they dissociate hydrogen, they're using the hydrogen lines and alpha lines, beta lines, and then also the emission of the argon try to measure that the number density in the plasma. So I show you what is the result here. So here that he plot that carefully about the electron number density as a function of time. This time is that the a pulsar plasma. You can see that the number density decrease quickly with that the progress of the time of the plasma discharge. But in this measurement, you can see that when the electron number density is very high, and 10 to the 17, so 10 to the 17 is very high electron number density in the beginning. So the method they used is that using argon emission, a method. And then when they go to very lower electron number density, and what they use is that they're using a line ratio of argon. So from hydrogen, a Stark broadening to line ratio, they are using this emission method try to measure that electron number density with a different magnitude. So this figure is very interesting. They're showing that uncertainty of electron number density measurement by using different methods. You can see that for example, using that a Stark line of argon, you can measure very high and electron number density. If the electron number density, for example, for equilibrium plasma, you really want to measure a electron number density, you probably you don't want to use that the Thomson scattering. The Stark line of hydrogen and argon probably give you a good measurement of that electron number density when the electron number density is very high. But however, in most of the non-thermal plasma, electron number density is rather low. It's between 10 to the 13, probably 10 to the 15 in this range. So in this range, you can see that is that the hydrogen beta line, and also that the line ratio of argon method can give you a narrow window. You can measure the electron number density. So I think that in the application, depending on what kind of a level of electron number density and you want to measure, you probably choose a different method. However, in most of the applications, that the number density in the plasma discharge is changing with time. It's very hard to say that are you using a different method for different number density. You probably have to use a combination of two different methods to measure electron number density. So this is something we try to share with you, and how to measure that the properties in the plasma. So this one is that basically to show you that how to measure that the temperature, particularly vibrational population in the plasma, in addition to the properties of electrons, electron temperature, electron number density, and electric field. Another one is that the distribution of energy in rotational, vibrational modes. So it's very important to measure how much energy is transferred to the vibrational mode, and how long does it take for the vibrational mode to be equilibrated in the system. So again, at a water Lampert and an Eagle, and measure this using a picosecond course, and to measure that the vibrational temperature. Here is that the experimental measurement. You can see the air is 100 Torr, and with a picosecond course, you can measure that the temperature of a nitrogen is dried air. You can see that for both nitrogen, and you have a first stage and a little bit of second stage, you have a faster heating, you have a little bit of slow heating, and then the diffusion basically draw cooling at the plasma. And for air, you have the fast heating and you have the slow heating. You clearly see you have the two stages. The question to ask you, why that the air, you have the faster heating and then second heating becomes more stronger than that one in the nitrogen? So yesterday we talked about what is the key mechanism of fast heating, right? It's basically involving with recombination of oxygen, excited oxygen, and oxygen ions, right? So that is the main thing for fast heating and the vibrational state. So this is why that the energy transfer that with air and nitrogen is different depending on mechanism of fast heating and slow heating. And then it's interesting that they did more exploration about the quantitative measurements, not only that the vibrational nitrogen and a transitional temperature and that the atomic oxygen, for example, this simulation, this is not a measurement. There's a, using a TALIF, you can measure a atomic oxygen, and they did it, and we did it as well. So this key information are really the key that to understand what is that the plasma properties. What they concluded that there is a strong vibrational excitation, particularly for nitrogen, from a 0 to 8, the state 0, and vibrational number of 0 to 8. And there is a early afterglow that we're using that the vibrational to vibrational energy change. So the vibrational high level becomes lower level becomes high level. So this is the vibrational energy transfer. And also that the vibrational transitional relaxation, for example, vibration level going down and then the atom getting hot. So this is that a clear indication that in the plasma this vibration non-equilibrium energy transfer becomes very important. And this also showing that the two-state heating, and it gives you the same feeling what is going on and in the plasma process. So therefore, that is the rapid heating, slow heating, and then vibrational transfer, and vibrational rotation, transitional energy transfer are the important process. So if you're looking at this experimental result, and you're thinking about how to build a kinetic model to model it for a non-thermal plasma, so it will be very important to consider this vibrational energy transfer, correct? But if you really want to do a plasma, let's say I want to do some kind of a plasma reforming or plasma ignition problem. So if you are a combustion guy and you want using a plasma to enhance ignition, do you care this vibrational excitation or not? Yes? Because of what? No? Because of what? You see, this nitrogen is mostly that this nitrogen involving this kind of a vibration. This, for example, this is only involved in a thermal process, isn't it? They are not really that the vibrational energy of nitrogen is high enough to dissociate any radicals, right? If we really want to care about the second heating, for example, slow heating, and you need the vibrational mode of nitrogen. If we really want to just consider about the ignition process, the number one important thing is radical production, right? The second issue is that heat transfer problem, right? So therefore, these reactions, for example, the nitrogen ABC electronic excitation is very important because they directly collide with oxygen and give you radicals. The first thing you need to consider is this, and then this probably the second order the things you want to consider and put in combustion process. Because the process is quite slow. You can see that take about 10 to minus 2. So, and then the non-equilibrium effect is not really that strong in terms of kinetic effect. Okay, so let's move on. So recently that there's James Michael at Iowa State, and he also introduced that the picosecond cars to measure that the vibrational and transitional temperature. What he did that he using, for example, using a 50-second laser, and to excite that they pump this one to the first a virtual excitation state, and the second one, and it generated this kind of a vibrational excitation. And he sent a probe laser and is measuring this the car signal. So this is that the plasma discharge. You can see that the electrode, that is another electrode, and try to measure that the distribution of temperature in the direction of a plasma discharge. You can see this is that the vibrational temperature, this is the rotational temperature. The difference probably is about 1,000 Kelvin, depending on the location of plasma. So what we try to show you that in a very well-designed experiment, today with that the availability of 50-second laser and a picosecond laser, you are able to measure that electrical field, be able to measure that vibrational excitation of molecules. And with that, probably a 10 Hz arc laser, you'll probably be able to measure using Thomson scattering to measure electron number density and temperature. Using emission spectroscopy, if we don't have anything, you can measure emission spectroscopy. And using argon line or a hydrogen alpha beta line and a stock broadening, you can measure electron number density as well, if we really need to. Okay? So this is just to give you some kind of overview, what can be done, what has to be done, and what are the range will be. And so then we move to kinetics. Question?
Just curiosity, in the vibrational temperature in the previous slide, why does it go back up?
This one?
Yeah.
So this is that, for example, this is probably the age of the plasma. If you have a very electrode, and then let's say this one, it's a sharp age, right? The electric field could be very strong in this age. So that could be a backup excitation, depending on the collision and relaxation process.
So it's excited, but without any luminosity?
Without? Yeah, luminosity is not vibrational, as I said before. Yeah. Luminosity mostly is generated using electronic excitation, or is the recombination between electrons and ions. That generates luminosity. Vibrational itself does not generate luminosity, and you can see by your eyes, because mostly infrared, right? Vibrational. Agree? Okay. And this is that this work is that the next thing we try to talk. What is that the kinetic process? We talked about the electrical properties, plasma property measurement, and then we try to think about what is the kinetic process in a plasma. I think this experiment done in France and by Professor Chris Laux. And so they're using a 10 nanosecond plasma discharge between the needle, and then drive it with a 5.7 kilovolt and then 10 kilohertz, and then the gap is 4 millimeter, and dump probably less than a millijoule and per pulse. And we put it here. And try to understand what is that the kinetic process of plasma. So what is the measure? The measure is that atomic oxygen, like using a 2-photon laser-induced fluorescence. And then they measure that the excited nitrogen using cavity rain-down spectroscopy, and using that the nitrogen B and C using emission spectroscopy, and temperature by using emission spectroscopy. And the electron number density is using the hydrogen beta line and stock broadening. So you can see that the previous techniques is some of them are used here. So this is a very interesting result, and this paper published in 2013. I think this is one of the major and milestone in a plasma-assisted combustion to understand what is going on and in a nanosecond plasma discharge. So if you look at here, that this as time equal to 0 is that the plasma short pulse. I have a nanosecond pulse and rising at time equal to 0. So you can see the measurement. You can see the measurement is that the first thing coming up is that the electronic excitation of B and C. So, and this is that because the emission spectroscopy is constant, you cannot measure the. So you can see that the electronic excitation of B and C is the first thing to rise. That means electron impact with nitrogen generates this electronic excited nitrogen. And this electronic excited nitrogen decay probably in about start from about 10 nanosecond, and after that the plasma power decrease. You can see that the voltage decrease here. After the voltage decrease, and immediately that this electronic excitation decrease. And then at that time, you can see as the electronic excited nitrogen decrease, at the same time atomic oxygen generated. So you can see before that, atomic oxygen really low. Electron impact generation of atomic oxygen has some, but it's very low. But after that, as the electronic excited nitrogen decrease, and you can see this one continue to rise. So this will give you a physical understanding the process. The first process should be that. So this is the first process is that the electronic excitation with nitrogen is generated electronic excitation of nitrogen. This nitrogen collided with oxygen, they generate atomic oxygen. So this is that the two-step mechanism proposed by Popov and in 2001, and first experimentally verified in a in situ laser diagnostics about the process. Okay, after that, I think that the in plasma modeling, people become more and more clear, and these two processes are really important and in plasma-assisted combustion. So let's take a break for 15 minutes, and then we come back at 3:15.